Hi, I'm Robert, and I'm back again to tell you some more about Bayesian statistics inside Stata software. I want to just take a couple of minutes to talk about algorithms, the mysterious inner workings of Bayesian inference. What we need to have in Bayesian inference is a sample from the posterior distribution of the parameters of your model given your data. And in order to do that, we need to have an algorithm that will run iteratively and generate a bunch of values for each of the parameters which, taken together, describe the posterior distribution. A handy way of thinking about it is to say that each of your parameters might form an axis, and they jointly define some sort of space, which we could call parameter space. And so the values make coordinates which relate to one point in parameter space, and the algorithm has to move from one point to another, sampling as it goes and making up the posterior distribution. So there's two algorithms that Stata uses: adaptive Metropolis-Hastings and the Gibbs sampler. And the adaptive Metropolis-Hastings works by a kind of random walk. Starting from the point that it's at, it's then going to move out a random amount in a random distance and try that point, and if it's better it probably stays there, and if it's worse it probably rejects it and goes back to where it was before. And if you do the probably accept reject step correctly, you end up with a sample from the posterior distribution, which is great. One problem though is that very often we end up with highly correlated posterior distributions, so they're very long and thin in parameter space, and just randomly heading off in a direction is actually very likely to take you out of the distribution into a lower probability region. And so a more efficient sampler is called the Gibbs sampler, and this splits the dimensionality of parameter space and deals with them one dimension at a time, or one block of dimensions at a time. So taking a slice through the posterior density in one particular dimension, you might find that in that dimension the distribution is something easy to compute off the shelf, like a normal density. And we know how to generate random numbers from a normal density, so we break down a complicated task into a series of simpler tasks in the Gibbs sampler, and that's why it speeds up a great deal. This is a scatter plot showing 10,000 points sampled from the posterior distribution of the constant term and slope from a simple linear regression. And the orange dot at the center is the first point sampled by the adaptive Metropolis-Hastings algorithm. As we let the algorithm run, we can see it's accumulating orange points. And once we have the first 500 points, you can see that they provide some information about the shape of the posterior, but they are not yet able to give information anywhere near as precisely as the 10,000 blue draws can. In contrast, if we look at the Gibbs sampler, we can see that it moves very rapidly from one end of the blue distribution to the other, and after 500 iterations it has a very representative sample. To use it inside Stata, you can just specify Gibbs as an option to your Bayes prefix or Bayes MH command, but you can only use it in certain circumstances where the model breaks down in a useful way, and you can read more about that in the Bayes manual. Thanks for joining me. If you want to upgrade to Stata 19, you're going to get a bunch of really powerful Bayesian functionality, and here's the link you need. And thanks for listening. Happy analyzing.